so that we can use substitution. And the reason that it's set up is because the substitution method requires you to solve for one of your variables, okay? Like try to isolate either the y or the x, and then we're going to plug this into this other equation, okay? Since this one's already solved for y, so y is equal to 2x. Taking this 2x, we're going to plug it in here, and then we're going to simplify and try to solve for x in the top equation. So we have 1/2 2x plus 2x is equal to 21/2. Okay, now I'm going to begin to solve it. First thing that I want to do is I want to get rid of this 1/2. That way I'm just left with 2x plus 2x on this side. So since it's 1/2 times this whole quantity, I can divide by 1/2, or that's the same as multiplying by 2. Okay, so that'll cancel out. 21/2 times 2 is going to be just down to 21. And I'm going to combine my like terms. So I'm left with 4x is equal to 21. Okay? Because when you multiply by 2, these cancel out. Left with just 21. That takes care of that. And it's pretty easy. If I divide by 4, I get x is equal to 21/4, or 5.25, or 5 1/4, however you want to look at it that way. But it was set up pretty easy for substitution, so that's the method that we want to choose. Remember, these all come from the SAT, and we want to be as efficient as possible anywhere as possible. Okay, so we can be one thing, we can be efficient. All right, that marker isn't the greatest, so we'll see, is this one any better? Not really. Lovely. Anybody want to send me some Expo markers? I would be greatly appreciative, but it's okay. Okay, so today what you have on tap. We're going to be lecturing. Get back to our things. Like I said, we're going to lecture. We're going to have homework. And then we'll take care of the self-evaluation on Wednesday, and then the mastery check on Wednesday as well. And we're going to keep operating, trying to knock out one section a week. We're going to start chapter 3, which kind of causes a little bit of an issue, and that's only because we're going to have Christmas break. So we'll be able to finish up chapter 2 today. On Monday, we'll begin 3:1. And then the following week will be 3:2. I'm sure your other teachers have told you that we are not having finals this year for the spring semester, so you will not have a calculus final or PreCalc final. So thank COVID for that. But actually that extra credit that was on McGraw-Hill from over Thanksgiving, that would have been basically the final I would have given you. That was cumulative over chapter 1 and chapter 2. So here we go without any further ado. So we have solved polynomial and rational equations. Those were lessons 2, 3. We didn't really get into too many of the polynomials in 2, 4. So that's because they bring up a whole lot of outdated methods like Descartes' method. What we're going to be doing today is solving polynomial inequalities. Okay, so a polynomial inequality is when we are going to take a polynomial and we're going to try to figure out what range is less than a specific number. Okay, so we're going to use algebra to kind of alter the equations to make it easier for us to find it. But in the grand scheme of things, it's pretty simple. And we're also going to solve rational inequalities. So what we just did, graphing rational functions will still come into play, and graphing polynomial functions will still come into play, because you can use Desmos pretty easily to help solve these. New vocabulary, you have polynomial inequality. You have a sign chart, which is basically the range and the areas of where our graph is positive and where our graph is negative. And we have a rational inequality. So polynomial inequality is a polynomial function compared against a simple number. A rational inequality is a rational function compared against a certain number. Okay, so it's like taking a parabola. We're going to have a horizontal line, and we're going to try to figure out where we are able to solve this polynomial. Okay, so here we have our first polynomial inequality. Okay, like I said, this is going to be, we could graph this and solve it pretty simply. Okay, but since it's a polynomial, we want to be able to use algebra, so we're going to be factoring quite a bit in this section, but it's not going to be the worst in the world. Okay, but in order to get it into an area where we're factoring, we want to get this inequality to where it's comparing to 0. Okay, and the way that we're going to do that is we're going to isolate. We're going to bring that 1 over to the other side. So we have x squared minus 8x plus 16 is greater than or equal to 1, or less than or equal to 1. So more or less, what values do we plug in, or what x values would we plug in? Would we get a y value or an f of x value that is less than 1 is what we're trying to find. Okay, so like I said, we're going to isolate and bring this 1 over. So after we do that, we're left with x squared minus 8x plus 15. And now that is less than or equal to 0. Okay, so now here's where your factoring comes in. Okay, factoring is going to reveal the real zeros. So the real zeros are where we're equal to 0. Okay, so I'm thinking of two numbers that are going to multiply to be a positive 15 that are going to add up to be a negative 8. Okay, the two that come to my head are a negative 3 and a negative 5. They multiply to be 15. They add up to be a negative 8. So this, in its factored form, be written as x minus 3, x minus 5. Okay, and the beautiful thing is, this gives us the ranges, right? We have real zeros. This is where this polynomial crosses the x-axis, which is what we're trying to find. So we know we have a 0 at 3. We know we have a 0 at 5. So this is building the sign chart. Okay, we have our zeros at 3 and 5, but I want to figure out if I go left of 3 or to a 2, am I going to be positive or negative? Okay, in between here, between 3 and 5, is it positive or negative? Because I'm comparing it against the x-axis right now. And if I'm greater than 5, is it positive or negative since I'm comparing it to the x-axis? So the way that we find that is we simply just plug in. Okay, we're going to plug in 2 into this equation. Okay, so 2 minus 3 yields a negative 1. 2 minus 5 yields a negative 3. Negative 1 times negative 3 is positive. It's positive 3. Okay, and I did that just by plugging 2 into my equation. Okay, now for my middle range, 3 and 5. One whole number that's in there, and you want to use numbers that are easy for you. That way you can do this pretty quick. So if I plug in a 4, 4 minus 3 is going to give me 1. 4 minus 5 is going to give me a negative 1. If I multiply those together, 1 times a negative 1 is a negative. So in the interior here, I have a negative. Okay, and for our last one, for our right range, because our zeros are here, so we're going to plug in 6. Make it simple. 6 minus 3 is 3. 6 minus 5 is 1. 3 times 1 gives me a positive 3. So I'm positive there. So now using my sign chart, where have I shown that the graph is greater than or less than or equal to 0? Okay, so that's going to be where my negatives are. But since it's equal to, also, I have to encompass 3 and 5. So I'm going to express my answer in interval notation. And that is going to be a bracket 3 to 5. 3, when plugged in, it's equal to 0. Okay? 5, when plugged in, it's equal to 0. So that satisfies the equal to. And since it's negative on the interval between 3 and 5, that is where my graph is less than 0. Okay, so this 3 to 5 would be my answer. Okay, in interval notation. But you can also do this using Desmos, like I said. So if I plug in, share my screen real quick. That way you guys can get a visual picture of what we just did. If I plug in y equals 1, that takes the right side. That takes care of my right side of my inequality, right? So now it's just up to me to plug in the left side of my inequality, which began as x squared minus 8x plus 16. Okay, and you can see visually where the range or where this polynomial dips beneath this line. Okay, so we're expressing this using interval notation. I'd recommend using Desmos, okay, in any situation that you can't factor it. Okay, factoring, because anytime we're graphing, it's always an estimate. Desmos is pretty cool because it'll show us our intersection. So we have 3, 1, so that's our equal to. We have 5, 1, and then the range between there is what solves our inequality or makes it true. Okay, in subtracting the 1, all that does is bring that parabola down, but it allows us to find the zeros in ways that we are capable. Okay, we could use the quadratic formula to solve these. Factoring, always a definite. Back to my screen. Here we go. Okay, so subtracting 1 from each side, you get x squared minus 8x plus 15 is less than or equal to 0. So factoring yields the real zeros. And we found, though, that we have a 0 at 5 and a 0 at 3. Okay, and then creating that sign chart, because after we subtract, we're just comparing to the x-axis. Okay, it's just shifting it down so that we're able to find our zeros, which allows us to build that sign chart. If we didn't find the zeros and didn't bring that over, we would have to plug in values to try and determine where exactly our graph y equals 1. Okay, Leah, so that's on this right side here. Okay, y equals 1 is just representative because that's the value I want to know that I'm beneath. Because my original inequality started out as x squared minus 8x plus 16. So y equals 1 just puts that horizontal line so I can see where my parabola dips down and comes underneath of it. Okay, that way it's kind of like a visual type of stuff because we're comparing it to numbers. We're comparing these polynomials to the numbers, and we're going to be comparing these rationals to a number as well. So being able to plug in that horizontal line gives you a very visual aspect of it. Okay, but after we brought it over, we were able to find our zeros, and then that's what allowed us to use just to be able to figure out if it was positive or negative, because once we brought that 1 over, we're comparing it to the x-axis. And wherever it was negative is going to solve our polynomial inequality. Okay? And they just break it down negative, negative that way. I actually multiplied it out. It's because when you plugged in a 2, you got a -3 and you got a -1. When you plugged in 4, you got a -1 and a +1. So that's the negative, 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 positive, positive, positive. When you multiply those, you end up with a positive answer, a negative answer, and a positive answer. Just like that. So because f of x is negative in the middle interval, the solution occurs between 3 and 5. So remember, we want to use interval notation. So whenever we're talking about less than or equal to or greater than or equal to, we're going to have brackets. Okay, if it's just less than or greater than, we're going to have parentheses. Okay, the same way that we would normally. Okay, here's a little bit tricky one. Okay, but we can handle it the same way. So what it's asking you is the polynomial x squared minus 9x plus 10, what x values, when plugged in, are going to be less than 46? X squared minus 9x plus 10. Okay, and this one is just less than. So since it's less than, as you can see from the answer choices, we're going to be using all parentheses. So we can't eliminate any answers that show brackets here. Okay, and you can also use in behavior and what you know about that polynomial to kind of help guide you. So we have an even leading degree with a positive leading coefficient. So we know that the end behavior is going to be going towards positive infinity. Okay, on both ends. And that comes straight from your power functions and what we've done previously with parabolas. So we know, well, this end's going to be positive and this end's going to be positive. So really, it's going to be that kind of middle section. That's the only way that it's going to work. Okay, because my left end behavior, as x goes towards a negative infinity, f of x goes towards a positive infinity. And as x goes towards a positive infinity, f of x goes towards a positive infinity. So I can kind of set up my answers and kind of determine exactly, I can get a good picture of it just by looking at that polynomial. Okay? But we want to do the same thing. We want to bring this 46 to this side so that we're able to factor to find our zeros, and then it makes it very easy because now we're just looking, okay, where's my graph positive? Where's my graph negative? Okay, and it doesn't materially alter this equation, it just shifts it down. Okay, it's going to shift it down 46 units. So if we subtract 46 from this side, bring it over here, we're left with x squared minus 9x minus 36 is less than 0. So now I want to see if I can factor, right? Does this polynomial have 2 real zeros? So I'm thinking of 2 numbers that multiply to be a negative 36 that add up to be a negative 9. And that's going to be x minus 12 and x plus 3. Okay, from here, I have enough information to really solve the equation. Okay, I know where my real zeros are. I have a real zero at 12. And I have a real zero at negative 3. Okay, and once again, in behavior determines that probably this side's going to be positive and this side's going to be positive as well. Okay, but we just plug it in to check. So when I plug in a negative 2 minus 12 gives me a negative 14. Negative 2 plus 3 gives me a positive 1. Multiply those. That gives me negative answer. Oh, duh. That's the interior. Negative 2 is in the middle. Duh. Helps if you remember your number lines. Okay, so negative 2 gives me the negative. Okay, if I plug in negative 4 for my left side, because on a number line, negative 4 is to the left of negative 3. Negative 4 minus 12 is negative 16. Negative 4 plus 3 is a negative 1. Negative 16 times negative 1 gives me a positive. Okay, a positive 16. And then if I plug in 12, or if I plug in 13, 13 minus 12 is 1. 13 plus 3 is also 16. 1 times 16 is a positive 16. So where on my intervals is my graph negative? And that's between negative 3 and 12. So the answer expressed in interval form would be parentheses negative 3, comma, 12. And I have to use parentheses because it's just less than. It's not less than or equal to. Okay, so I want to not encompass negative 3 and 12 because that would not make my inequality true. So it should be negative 3 and 12, which corresponds to answer A. Getting good at this. Okay. So the next one. Now I'll bring it up. But this is one that I would recommend using Desmos. Okay, Desmos is going to be the most efficient method. Okay, so we're trying to solve x cubed minus 22x, and where is that greater than 3x squared minus 24? Okay, so like I said, we're going to end up using Desmos here. But if you look at, if we just plug it into Desmos, you're going to see that it kind of looks like a jumbled mess. It's 22x. And then 3x squared minus 24. Okay, and I'm trying to figure out where on my graph my blue is greater than, or where on the graph my red is greater than blue. And you can see looking at this, it really, it's not really a clear picture, right? So what I'm going to do is I'm going to end up altering my polynomial and bringing this 3x squared minus 24 to that side. Okay, and that creates one giant polynomial that makes it a whole lot easier. Okay, so you can see once I've done that, I'm going to end up with x cubed minus 3x squared minus 22x plus 24. And where is that greater than the x-axis? X cubed minus 3x squared minus 22x plus 24. Okay, and what intervals is it greater than the x-axis? Where is it positive? So you can see I have a real zero here at negative 4. I have a real zero here at 1. And I have a real zero at 6. Okay, and I'm going to analyze my graph to determine what exactly is going on. So left-in behavior here you can see that it's negative. Okay, but the question as it was written, I want to figure out where I'm greater than the x-axis. So where is that graph positive? So since it's negative, from -4 to -infinity, that is not going to be a solution. Okay, and I'm just building a sign chart on the whiteboard. Okay, so left in behavior, I stay negative. That middle part between -4 and 1, I'm positive. But then between the real zeros of 1 and 6, I'm negative again. And then from 6 to a positive infinity, I'm positive. Okay, so now I want to express that in interval notation. Okay, and I'm going to be using parentheses because the original inequality was just greater than. Okay, it's not greater than or equal to. Okay, but my solution occurs here and it occurs here. So in interval notation between -4 and 1, with a union of 6 to a positive infinity. Okay, and we can do that anytime that we don't have a factorable option. Okay, you can use the graph, but it's always just an estimate. And you want to manipulate the inequality to make it easier for you to solve. If you saw that first graph, that kind of looked like a jumbled mess. But once it got clearer, then the picture became clear and it became a pretty easy problem to solve. Okay, so another one. Solve 2x cubed plus 9x squared, which is greater than or equal to 3x plus 4. So first thing, once again, I want to bring everything to that side, and I want to see if it's a factorable polynomial. So I'm going to be left with 2x cubed plus 9x squared. That is going to be plus 3x because it's a negative on the right, minus 4 greater than or equal to 0. So that's the polynomial I'm going to be working with. That's after it's altered, after I've shifted everything to the right. And now looking at that, is there a greatest common factor that I can factor out? No, not really. Okay. Could potentially factor that by grouping. But this one, the most efficient method is to plug it into Desmos. Two x cubed plus 9x squared plus 3x minus 4. Just dumb. Zoom in a little bit so we get a better picture of it. Okay, and I'm looking for my real zeros. So I have one at -4. I have one at -1. And then I have one at 0.5 or 1/2. So using in behavior again, -4 going to -infinity in terms of x values. I'm just going to be going farther and farther negative. Okay, between -4 and -1, where my positive occurs. Between -1 and 0.5 is where I dip back beneath the x-axis. And then from 0.5 to a positive infinity in terms of x values, I'm positive. Okay, and I want to list the positive intervals in interval notation. Okay, so just built the sign chart. So that is going to be the bracket between -4 and -1 with the union between negative or 0.5 comma infinity, and the infinity gets the parenthesis. Okay, and I use the brackets because I'm greater than or equal to. Okay, but the infinity sign is unbounded, so that is a parenthesis always. So my correct answer is C. Or. Dang it. Dang it, dang it, dang it. Okay. So polynomial inequalities with an unusual solution. Okay, because they're not always going to be clear. They try to throw you a couple curveballs as well. So we're dealing with x squared plus 2x plus 3. And where is that less than 0? Okay, this one seems like it should be a pretty easy question, right? We should be able to factor it, find the zeros, build our sign chart, and be on to the next. But looking at it, I'd have to find two numbers that can multiply to be a positive 3 that would add up to be a positive 2. Well, the only things that multiply to equal 3 are 1 and 3. Added up is a positive 4. Okay, even -1 and -3 would still give me a -4. So this is a prime polynomial. This polynomial has no real zeros. Okay, and since my value of A is positive and my end behavior goes up, this has no real zeros, so it doesn't touch the x-axis because this is a prime one. So since it has no real zeros, there's no area of this graph that dips beneath this x-axis. It starts above and it finishes above. So the answer is going to be no solution. Okay. Here, it's the same polynomial. So it's x squared plus 2x plus 3. Once again, it's prime. And same with the last equation. It has no real zeros. My A value is positive. My leading degree is even. So in behavior, they both go to a positive infinity. Okay, so this one, instead of being no solution, is the last question asked, where are we less than 0? This one should be all real numbers because the graph starts above 0 and it finishes above 0. Okay. So, last one with unusual solution sets. We have x squared plus 12x plus 36. So trying to factor this, there are two numbers that multiply to equal 36 that add up to be a positive 12. Yes, there are. Okay, and those are x plus 6 and x plus 6. Okay, or x plus 6 squared. So factoring that would reveal x plus 6 squared, which means that this only the vertex touches the x-axis. And since we're greater than 0, it's not going to be all real numbers. It breaks it into the union between a negative infinity to a -6. the union between -6 and a positive infinity. And we have to use the parentheses because the solution of -6 is equal to 0, because that's our only real 0 that we have here. So that would violate the inequality. If it was x squared plus 12x plus 36, where is it greater than or equal to 0? It would be all real numbers again. But since it's just greater than, -6 has to be left out of that interval. Okay, but once again, you could factor that. You could graph this to show it in Desmos. This should be a pretty simple section for you guys. It's not typically the most, it's not typically the hardest in the world, but it's kind of makes you think. It's a hard concept to wrap your mind around. But if you break it down to its base terms, we're given a polynomial or a rational function, and we're comparing it to a specific number value. Where is it greater than that number, and where is it less than that number? Okay, if you think about it in those terms, it's pretty simple. Okay, so here we have the same polynomial again, x squared plus 12x plus 6. Once again, the factored form would be x plus 6 squared. So the only real 0 we have is -6. And here we're comparing it, where is it less than or equal to 0? So since the only real 0 we have is -6, our graph ends behavior is going to go towards a positive infinity because our a value is positive and our leading degree is even. The only number that satisfies this is going to be -6, because that's when we plug in -6, we get our 0. Okay, so x squared plus 6x plus 9. Okay, this one, once again, is going to be one of those ones that breaks down to x plus 3 squared. Okay, so it's 1, 0. So the vertex is on the x-axis, and we can find that by factoring, because 3 would be the only number that 3 times 3 multiplies to be 9, and they add up to be a positive 6. So x plus 3 squared is what we're looking for. So in this one's determined based upon where, I clicked onto the wrong thing, where exactly are we greater than 0? So we have a 0 at -3, it's the vertex. So, and because the end behavior is positive and it's a parabola facing up, the answer is going to be D. Because from -infinity to a -3, we're above the x-axis. We hit -3, and then we shot back up to be -3 to a positive infinity. And since it's just greater than, we have to eliminate -3 from our solution set. So the answer should be D. -infinity to -3 with a union between -3 and a positive infinity. Okay, so here we want to solve a rational inequality. Okay, rational inequalities, we're going to do this primarily by graphing it. Okay, where do we fall beneath the x-axis in this case? Okay, so analyzing this graph, we know we have a vertical asymptote at -2. Okay, because if we were to just isolate the rational function in itself and try to graph that. So in this case, m is equal to n. So that says that our horizontal asymptote should be at the leading coefficient of 3/1. Okay? So we should have a horizontal asymptote if we were to just isolate this rational function. So not even considering that -3 at this time. Because all that does is it takes that rational function and it drops it down. Okay, when we were graphing rational functions, it was always just expressed as like 3x plus 4 over x plus 2. So if we list out some information that we have on this graph, we have a vertical asymptote, at -2. So if I come over to my handy dandy board, -2, that's where my vertical asymptote occurs. And that's because -2 is the only answer that makes it undefined. Okay, my horizontal asymptote, once again, that's done by comparing our degrees to each other. If they're equal, then it states that we should have a horizontal asymptote at where the numerator's coefficient divided by the denominator's coefficient. So that would be at 3. Here's where it causes you an issue. Okay? At 3, and that's because we have that -3. What that does is it shifts that horizontal asymptote down. So now our horizontal asymptote is at the x-axis. Okay, and that's really the only addition that changes to these rational functions. And then I'd want to plug in, from -1, I'd want to plug in like a -3 or a 0 to really set myself up pretty simple. So if I plug in -3 into 3x plus 4, I'll write it up, 3x plus 4x plus 2, that's -3. Okay, if I plug in -3, 3 times -3 is a -9 plus 4, that's a -5 on the top. Okay, -3, -5. -3 plus 2 is a -1. So -5 divided by -1 is going to be a +5 minus 3 is 2. So that point is going to be right here. Okay, and then going to the right of my horizontal asymptote, the easiest one to use is 0. So when I plug in a 0 into this equation, I get 3 times 0 is 0 plus 4. Okay, so that's 4 on the numerator. 0 plus 2 is equal to 2. So that simplifies down to 2 minus 3, which is going to be equal to a -1. So I have the points -3, 2, 0, -1, right there. And because my horizontal asymptote has been shifted down to the y-axis, to the x-axis, my graph is going to look something like that. Okay, and that's the graph of that entire function inclusive of the -3. So I ask myself, where is it greater than or equal to 0? Okay, so that bound is going to be from a -infinity to a -2 with parentheses in interval notation. Okay, and I have to use the -2 because that's where my horizontal asymptote is. So I approach that value, but I can never touch that value. So that makes my equation undefined. My chair's in the middle of where I wrote it. But this here should be our answer. From -infinity to a -2. All right, let's see if I'm right. See how well Burns is doing today. How did I do that? Negative. Dang. There we go. So from a negative infinity to a negative 2.